Okay, so I'm going to be talking to you today about the consensus problem in distributed computing. Consensus is a fundamental and probably the fundamental problem in distributed computing. When you know that your system can solve consensus amongst some number of processes, that's able to tell you something about the computational power of that system. Before I actually introduce the problem, I need to make sure that we're on the same page, and that means I need to provide a model for this presentation. So like Dan mentioned, a model clarifies assumptions about three different things: synchrony, communication, and failures. You have independent processes. These independent processes are going to be taking steps. Are these steps coordinated in some fashion, or are they happening at arbitrary delays? There's some communication that needs to happen in order for independent processes to solve problems. This communication can be through shared memory, or through message passing. And finally, failures. What kinds of failures do these processes exhibit? Just like in Dan's model, I'm going to be assuming a asynchronous environment where processes are communicating through shared memory, and they exhibit crash failures. What that means is at some point in the execution, a process may stop taking steps permanently. So what is shared memory? Shared memory means your processes communicate using shared objects. To think about a shared object, it has two components. One is a current state. Originally, it's in its initial state. And it also has some operations that processes can perform on it. These operations, when applied, change the state of the object. So some examples include the fetch and increment object. This has a single atomic instruction, which is the fetch and increment instruction that was introduced. So suppose you have two processes. If one process calls fetch and increment to the fetch and increment object that's initially in state 0, it will get back the value 0, and the state changes to 1. Similarly, another object will get back the value, calling fetch and increment will get back the value 1, and the state changes to 2. There's also another example, the stack. So the stack has two operations, push and pop. Push appends something or places something to the front of the list, pop removes it and returns that to you. So suppose you have it in the initial state. If you push 1, if a process pushes a 1, it gets back some acknowledgement, and the state changes to reflect that the 1 has been pushed. Similarly, if it pushes a 5, the 5 appends to this front, and a pop will return the element. So that's what a shared object is. And now that you understand what a shared object is, we can introduce the consensus problem. So for n processes, the consensus problem is as follows. Suppose you have n processes, and they're each given an input. These are the input values. They can be different. They can be the same. And what they have to do is they have to use the shared memory somehow. So they have to communicate using shared objects in order to decide a value. They each decide a value, and this value satisfies three different conditions. So firstly, every correct process, and by correct I mean one that doesn't fail, decides a value. Agreement needs to be satisfied as well. So if two processes decide a value, they're deciding the same value. And finally, validity. If a process is deciding a value, then this value needs to have been in the input to some process. This is just that last condition, validity, is just to make it non-trivial, because without validity, a trivial algorithm would be decide the value 1. But that algorithm wouldn't work with the validity condition. Suppose every process had input of 2. That algorithm clearly doesn't satisfy the validity property. Why is consensus important? Well, if you take it at its bare bones, consensus means agreement. If processes can agree, they can actually accomplish a lot of things between themselves. So one very important property of consensus is called the universality of consensus. If n processes can solve consensus amongst themselves, then they can implement any shared object between those n processes. And that's a very powerful thing. We won't be going into too much detail about that, but you can ask me about that afterwards. So one really interesting question that you can ask about, or use about in the shared memory model, is if you're given a shared object O and you have n processes, can those processes use instances of that object O and registers to solve consensus or achieve consensus amongst themselves? I'm going to illustrate this with one object that I used in my research. This is called the QR object, and it's got two operations. It's a very simple object. The first operation is called compete, and the way it works is the first compete operation will return a win, and any other compete operation returns a fail. It's also got a query operation, and the way query works is originally all query operations will return a fail. Then at some point, some compete operation will get a win, and the R query operations that happen afterwards will return the identity of the winner. And finally, after you've exhausted those R query operations, any query operation after that will return a fail again. So it's an object that can host a competition and then is able to provide you the answer to who won the competition for our processes that call query. So the first thing I want to claim is that if you have R+1 processes, they can use a single QR object and R+1 registers to solve consensus amongst themselves. And intuitively, this should make sense. We're going to look at R equal to 3, so we're going to, but this can be abstracted to any R, any R in the natural numbers. So suppose you have R equal to 3, so suppose you have R+1 for processes, and you've got, each one has got an input value. Suppose you also have 4 registers, and you've got a Q3 object. So the way that you can solve consensus, or one way, is you can have these processes write their, or store their input values into the registers. This is called announcing their values. Once these values have been announced, we notice one thing. If we can, amongst the 4 processes, if we can elect a leader, then each of the processes can just read that leader's register and decide the value of that register. But how can they elect a leader? They can't predetermine this leader. Suppose they'd predetermined that process 1 was a leader. In that case, consider an execution where process 1 crashes before it takes any steps. That means process 1 crashes before it communicates its input value. So all the rest of the processes will be stuck waiting for process 1 to put or announce its input value. So clearly, it has to be from amongst the announced or the processes that have announced their value that we have to elect a leader. How do you do this? Well, you just use the Q3 object. The way it works is you call compete on the Q3 object. One will get a win, the rest will all get a fail. And the winner can just, it's the elected leader, so it can just announce it or decide its value. This is process 2 in this case, deciding a 5. And the rest, you have 3 other processes. What do? They just query for the identity of the winner. They read the winner's register for its announced value, and they finally decide that value. This is very simple, but can we, suppose that we had another process as well. Suppose we had 5 processes. Could we use the same approach? Actually, it's not very easy to see that you can actually solve consensus for using a Q3 object for 5 processes. But and the reason it's not so easy to see is if in this case you had 5 processes, the 5th process, if it performed another query, would not get the value of the winner back. It would get a fail because the Q3 object is queryable 3 times. So how can R+2 processes solve, how can 5 processes use Q3 objects and registers to solve consensus? Now, suppose you have 5 processes again. They've each got their input values, and you have 5 registers. Instead of a single Q3 object, suppose you now have 4 Q3 objects. How does this make a difference? We can start off in the same way. We can start off with each process announcing their value in their registers. After they're done that, what do? In a similar fashion, they want to compete at the Q3 object, the first Q3 object, to elect a leader. So they've elected, in this example, process 4. Process 4 is the leader, and so he can just decide his own value. Now, what do the rest of the processes do? They can't query the first Q3 object directly because there are 4 processes, and the Q3 object is queryable only 3 times. To solve this problem, we can have the rest of the processes first compete at the next Q3 object. One of them will get returned win, the rest will be returned to fail. The winner can then go on to decide his value by reading the Q3, or by querying the Q3 object for the winner's value. It would get back the identity of process 4. It could then read process 4's register and decide that value. The rest of the processes move on to the next Q3 object. In a similar fashion, the winner of this Q3 object will query the first Q3 object to get the identity of process 4, read process 4's value, and then decide that value. And the remaining two processes will look at the last Q3 object. And again, similarly, the process 1, which won that last one, will query the Q3 object. In this case, note that we've now exhausted the first Q3 object in queries. And process 1 can read the 8 in the register and decide that value. What does the last process do? It's not able to directly query the first Q3 object, but what we have now is the ability to deduce who is actually the winner. Process 3 knows that it's not the winner. It also knows by querying the second Q3 object that process 2 is not the winner. It can query the next Q3 object to learn that process 5 is not the winner, and similarly that process 1 is not the winner. From that, it deduces that process 4 is the winner, and it uses this information to read the register associated with process 4 and decides that value. So this is a very cute algorithm because I think that it's not obvious at first. And this is why I wanted to illustrate it with this object. So consensus is a very important tool in distributed computing. And to learn more about it and distributed computing in general, you can check out the graduate courses that are offered at U of T. To enroll in graduate courses, you need to talk to the undergraduate office. And yes, so thank you.